Alright, hello, Mr. Dr. Padilla. Sorry about that, Dr. Padilla. I'm Joel Guzman, and I'm going to be presenting our project for the final, or test 3 actually, for Physics 46. And it is on the effect of the angle of incidence on the energy produced by a photovoltaic cell. This is a project that we decided to do because there's so many solar cells out there. Most of them are fixed, though, on the side or top of a roof. And we thought that it would be a good idea to see if by rotating the solar panel we'd actually increase the efficiency of the solar panel per unit area. So we decided we would grab a hold of a solar panel and we would rotate it so that it's perpendicular to the rays of the sun and see if it produced more energy than it took to rotate it. On that note, the procedure was very easy. We got a multimeter, set it to the amperage setting, connected it right up to the solar cell, measured the output to determine the solar angle. What we did is we could estimate it, but that wasn't good enough for Physics 46 because we want exact results. And so what we did is we went on Wolfram Alpha. That one tells you, this website, Wolfram Alpha, tells you the elevation of the sun at a specific angle for a specific time around a specific point on Earth. And it is very exact, up to seconds of a degree. So we used that. We recorded the information or the data 3 times on 3 different days. As you can see from the graphs in our report, the current as a function of time was consistently higher for the one that was angled toward the sun. On the same days, it was always higher. The difference as a function of time, the difference between the 2 currents, i.e. the flat current, when the panel is flat on the ground, and the current when the panel is angled, were always different, but the difference was greater in the morning and in the afternoon, more so in the afternoon. So if we were trying to maximize the effect, we would increase the amount of times that this being rotated, or its efficiency, by only moving it maybe in the afternoon. But as we will see, that's not really necessary. So the way that we calculated it was we had to propose a path along which this solar panel would rotate. In our instance, we decided to move it in a circular radius of 9 inches, or 0.2286 meters. Each movement, once every hour, would last 3 seconds. From that, we calculated the acceleration it would exert onto this item. And so we proposed starting at 8 in the morning and ending at 5 o'clock in the afternoon, with the machine staying at that last position until 30 minutes after sunset. After that, it returns to its original point in the sky, on the mechanism, in expectance for sunrise again the next morning. So in the report is a path of the proposed mechanism, the path it would follow in 1 day. After that, we use the power formulas that we learned in our electronics class, Physics 46, to calculate the average power. And then we calculated the average power resulting only from the difference between the 2 amperages. So using that, we determined that there was an average energy, extra energy, only from rotating it, of 8,128.5 joules. So that's only the difference. To power the mechanism, we calculated that it would take about, 2.64 joules. If we multiply that by 3 for any resistance against, friction, maybe a CPU to run and tell the machine when to move, we multiplied it by 3, so 7.9 joules. More than enough energy was created to run the machine. in the end, this is very, very important discovery or insight into the efficiency of solar panels, because it allows us to reduce the amount of area that is used for solar panels so that the fauna and flora on solar farms is not so affected. We can maximize the amount of energy produced by something so that costs come down. And we can also, because these things aren't sightly, we can learn more efficient ways of using them in smaller spaces. So for our report, we exploited this variable and came out with very, very favorable results.